Swayam Prabha. Digital India. Educated India.
Okay, so the construction goes like this. So you're given right. So we're going to have a vertex, and I will have x1, x1 bar, x2, x2 bar. These are vertices of the graph. To start with, right? Just by looking at the variables, these are my vertices of the graph. Clearly, there are, this is 3 colorable, right? But important thing I want, see, what is my goal? I want, the goal is that f is satisfiable. I want to show I want to construct my graph in a way that that's my goal, right? So in particular, from a 3 coloring, I want to be able to get a what? Satisfying assignment, right? So from a 3 coloring, I want to be able to get a satisfying assignment. So in particular, so let's call the 3 colors as 0, 1, 2. Okay, and without loss of generality, I color this vertex as color 2, right? It has to get some color, call it color 2. Then what do you know about the color for the remaining vertices? Xi and Xi bar must be 0 and 1. And more importantly, if Xi is 0, Xi bar must be 1, and if Xi is 1, Xi bar must be 0. Good. This is some property I want to satisfy, right, on my satisfying assignment. So that is ensured here, right? I don't want both Xi and Xi bar to get the same color. Then I will have a problem of getting a satisfying an assignment here. So that is the minimal sanity check we are trying to do in this gadget, is that every variable and its negation will get different colors. In particular, it will get 0 or 1. So this is my construction just for the variables. Now for the clauses, I am going to construct the following. Okay, so actually we are going to call this some let's say this vertex has a name, I am going to call it red. Okay, and I will also have some 2 more variables, true and false. These are just colors, names if you want to call it, and I am going to make these. Let's say my 3 colors are red, true and false. Okay, it will be easier for me to translate it to an assignment here. Okay, so if this is my coloring, clearly red must get a color which is different from true and false, and hence each of the Xi and Xi bar must get, one of them should get a true and another should get a false. Okay, that's why I am doing this construction. So now for a clause, here is my construction. This will look like a Boolean circuit for you. So suppose I have a clause which is X or Y or Z. 3 sat. Now each of this can be a bar. Okay, just for simplicity, I have assumed it is X or Y bar Z. Y could be X7 bar, Z could be X25 bar, any of this. My graph construction will look like this. This is separate for this class. Yeah, so this is my, for every such clause. So this, this x, y, z are actually these variables. I'm not making a copy here. It will be exactly, there is a vertex corresponding to every variable and its negation. So they are fed into this. Okay, this is looking like a Boolean circuit you look like, but we'll see why. Okay, these gadgets are carefully constructed. These are not very easy, but it requires work to construct it. But once you have it, you can verify this. So now I have basically 5. One thing I forgot to mention in the earlier construction, which is very important all the time, that the time it takes to do your construction should be polynomial. Okay, they are obvious, but sometimes again there is an exercise in the problem sheet which makes you pay attention to that part, that whatever construction you are doing from your source problem to your current problem, the construction time should be polynomial. Okay. I mean, in this case, it's not very hard to see that we are doing some n plus m, n square vertices, m cubed edges kind of things. Okay, so number of vertices in my graph is 2n, because there are n variables for xi and xi bar, plus this red true false, that's 3 more, plus for every clause I am adding 1, 2, 3. So this is C1, C2, C3, C4, C5. Okay, these 5 vertices are special to this clause. These are not separate vertices, these are the same x vertices from here. Okay, if it is x bar, you will pull out the corresponding x bar, otherwise you pull the corresponding x and add it to these 5 vertices. So number of, okay, let me just call it n prime, which is the number of vertices in G, is 5 into m. And you can calculate the number of edges also. Okay, so now this is my complete construction. Is the construction clear? Let's just take stock of what is happening. There are n variables, so I have this 2n vertices plus these 3 vertices that would correspond to my variable gadget in some sense. For every such clause, I am going to draw this gadget. These x, y, z are those variables, those vertices which are corresponding to the corresponding variables. And these guys are adjacent to the seat, true. And you do this for every clause, right? So for a next clause, the variables may be same. I will pull out from these variables. I will add these 5 extra vertices corresponding to that clause, and these variables will go in there and they feed it to this vertex. This is my big graph. Maybe should I do an example? Okay, why don't we do this example, right? So examples get very messy, so there are 6 I don't think it's going to be very more illustrative than the general picture I have, so I'll stick to this. Okay, I need some 3 times this board to actually draw this, and not necessarily sure that it will actually help you understand. Okay, so now what do I have to show? So I have this huge massive graph. Well, massive, it just has some 2n plus 3 plus 5m vertices, some maybe some linear number of edges, not too many edges. And what do I have to show? The graph, the formula, original formula is satisfiable if and only if this graph has a 3 coloring. Okay. Okay, so let's do one direction. So much of, everything boils down to a core of this gadget which I have constructed for a clause. Okay. So suppose f is satisfiable. What does that mean? there is a satisfying assignment for the variables x1, x2, xn. Now I want to color my graph with 3 colors. Let's call the colors as true, false and red. How do I color the graph? At least this part of the graph, how do I color? Whatever variable is assigned true by that satisfying assignment, I am going to give that variable true, its negation false, and that will actually satisfy all of these constraints, no problem with that. Okay. Now I want to show that there is a way to do this coloring of this gadget so that it is actually a 3 coloring. There is a way, in fact, okay, and my coloring, but I know that this clause C is satisfied by an assignment, right. So that means one of these variables must be true. So I will run through all possible combinations and I will argue that you can actually color them with these 3 colors. Let's pick some one assignment. Let's say is y got true in my overall assignment which satisfies all the clauses. Let's even assume that these 2 variables got false. I am going to give you a 3 coloring of these vertices. Okay. So what should this vertex get color? What? C5. What color should it get? If there is a 3 coloring, I want to give a 3 coloring. Red. Why? Because it is adjacent to a vertex with F and true. So it is forced to be red. Good. C4 is forced to be false. Now I have a choice of these 3 vertices and I want to argue that there is a way to do it properly, right. So maybe there is more than one way to do it. Yeah, so I'll just give C3 red, F as true and this is false. So I've given you a 3 coloring of these vertices, a proper 3 coloring of I did it for one clause, but since every clause has the key property I have used, which I will prove now when I get to the converse, is that one of this, so all the variables are colored with true or false and one of this is necessarily true. Okay, and that is all I need to show that there is a way to extend this coloring so that every other guy gets one of the 3 colors and graph is 3 colorable. Okay, let's see why. Suppose all of these are false, then I will argue that there is no way you can give a 3 coloring. Okay, so here the coloring is more or less clear, right? One of them gets true, one of them gets false, and that would correspond to an assignment. Okay, and this is red anyway. So the question is about this gadget. So let's draw this gadget again, and I will argue that if all of these are colored F, then there is no way you can get a 3 coloring of this. Okay, so let's look at the gadget again. Suppose all of these are colored false in my literal that's coming in, then this vertex is forced. What color? Red. This is forced. False. Okay, now I have choices here. Let's see. Excellent. Great argument. So he says you need 3 colors for this triangle. So one of them should use F, but they have adjacent F, so you can't do it. Okay, so we have actually more or less proved the converse also. So what is the converse? If there is a 3 coloring of the graph, then in each of these gadgets, one of them must have been colored true. Because if all are false, we just argued that this you cannot get a 3 coloring. So one of them must have been colored true. So you can pull out a satisfying assignment because whatever variable was true, make that true, other as false, and you will get an assignment that will satisfy every clause, because in each of these clauses one of them must have been colored true. Yeah, so this gadget, very carefully constructed to ensure this property. Now, if you just look at it, this is just 9 vertex graph. Okay, so somebody actually came up with this 9 vertex graph and said that here, if all of them are one of these kind of colors, then you can't be able to push it, and that gives you an idea of how to construct your clause gadget and how to reduce from SAT to 3 color. Okay, so, and this is what makes this theory very nice, right? That if you want to know whether a graph is two colorable, there is a linear time algorithm, not even polynomial time, because you can just do it in linear time by doing BFS. But if you want to know whether a graph is 3 colorable, the complexity increases. The best known algorithm we have take exponential time, and the problem is NP hard. Okay, last example I am going to do is some sort of a numbering problem, but it's also knapsack related to knapsack problem. So, but I will phrase it like this: subset sum. So, what's your input? Is a set of numbers. Some n numbers are given to you, and a target W. And the question is, does there a subset S prime such that sum of the W I in S prime no, this is not a correct mathematical notation, such that the weights in S prime add up to W. So, the knapsack version is a slightly relaxed version. I mean, so this is asked. Okay, so let's see an example. Okay? So, I have this set So, this is my set S, set of some numbers, and my target weight is 150, and I ask, is there some subset here, subset of these weights? If you add them all, they should add exactly up to 150. Is there some subset? 75, 12, 63 adds up to 150, right? So, now what would be an algorithm for this? Can you just tell me a brute force algorithm? Go through all the subsets of S, add the weights, see whether they add up to W. Adding the weights is just a linear time, but the number of subsets is 2 power n. Right? Remember, you gave me a complete, general, precise algorithm, and we quickly analyze it, right? And it's correct. It's correct because you're running through all subsets, fits in the definition. If there is a subset that adds up to W, you get. So, it's a 2 power n times some n kind of an algorithm. So, okay. So, now you can try some greedy. Okay, so the knapsack problem, which is slightly relaxed version, is that there may not be some subset which adds up to 8 W, but give me a subset that adds up to as close to W as possible. Right? Think of it as you have a knapsack, and there are some objects left, each one has a certain weight. Knapsack is a capacity, and a thief wants to steal as much as possible so that he or she can fit it into the knapsack. but we'll stick to this exact version, but that problem is also related. Now, so first thing is you can think of some greedy algorithm, right? So a greedy algorithm where you want to pick as much as possible so that it fits into W. What would be a greedy algorithm? You pick the largest weight, put it in your knapsack, keep doing it, right? And then pick the largest weight that fits into the remaining capacity, keep adding it. One algorithm. Maybe you want to do in the opposite direction, start with the smallest weight and keep adding it. Both of them don't give you optimum solution. Here is a simple example. Suppose my S is right. If you start with the largest weight and take it, how much can you take? Right? If you take the largest weight and put it in your knapsack, you will pick W by 2 plus 1. That's it. You can't take anything more. You are exceeding the capacity. But that's not the optimum solution because you are better off picking the 2 W by 2 guys. Right? So here's a simple example that this greedy, first of all, when you say greedy algorithm, there is no the greedy algorithm. Okay, you have to also specify what is your greedy choice. Taking the smallest weight may be a greedy choice, maybe the largest weight may be a greedy choice, but you can come up with examples where either of them won't give you optimum algorithm. Okay, but before I show NP hardness, I want to come up with an algorithm which is better than 2 power n. 2 power n times n was the algorithm we saw, but I want to give you something better than that using dynamic programming. Okay, so my is also a good drill on an example on dynamic programming, which is an important algorithmic paradigm. So my S has and my target is W. What is the key thing about dynamic programming? You have to figure out what are the sub problems we want to compute, right? And then we get to optimum substructure. What are the sub problems we want to compute? How do we recursively formulate the problem? And then everything will fall in place. Okay. Hopefully you've seen a lot of dynamic programming algorithms. Let's look at the last object with weight Wn. Okay. Either I take it or I don't take it into my solution. Okay. Now, dynamic programming is also going to explore all solutions. So, in a very systematic way, so the correctness will not be a problem because I'm going to explore all possible solutions and use the optimum substructure property. So, either I take Wn or I don't take it. Okay. So, let's go back to the knapsack version of it where I want to find the maximum close to W which I can achieve by a subset, and if it equal to W, then I know I have solved the exact version as well, right? So let's say the maximum weight, I don't want to use W, already used. Maximum capacity from on to n in my capacity W is, if I take the last object, suppose this is my notation, right? Max weight possible from a subset of 1 to n. And I want to write some recursive formulation based on, let's say, I take the last object or I don't take the last object, right? So if I take the last object, then what is the maximum weight possible in this notation? C of n minus 1 W minus Wn, right? How much does the weight reduce from? Because I picked the last object into my knapsack. So my residual weight is W minus Wn. pick the maximum possible subset from 1 to n minus 1. Is that all or anything more? Plus W1, because I have added W1. And if I decide not to pick W1, then it is C of n minus 1 W, and whatever the best I can get. This is it, right? The key thing is, how do I write a recursive formulation? After that, it tells you what are the sub problems you need to compute. Do it in a bottom up fashion and you will get the answer. And you have to prove that this equation is correct, and that's not very hard to show. The maximum capacity possible is that either you take W1, if you manage to take W1, then from the residual capacity pick the maximum possible from the remaining subset. If you don't pick W1, then pick the maximum capacity. Full capacity is available, do it from n minus 1. So now what are the sub problems we are going to compute? These are the sub problems for different values of n and different values of W, right? We go slowly from small values of W, small values of n. The base case would be like C1W or something, right? If your first object has capacity W, then that is the best one, and you gradually, using this recursive formulation, you will compute finally what is the maximum possible thing available using any subset of n objects. Okay, this has the optimum substructure property which is used here, that if you pick Wn, then whatever remaining is the optimum solution from 1 to n minus 1 in the remaining capacity. So how much time does it take to run this algorithm? N into W, right? Because now you start W from 1, 2, 3 up to W. Assume that your weights are all integers, right? Let's make life easier, because otherwise we have to deal with fractions. So now I just start with weight 1 with weight 1, how much can I get? With weight 2, how much can I get? Go all the way up to W and vary your n also, and to compute CNW, you should have computed Cn minus 1 this and Cn minus 1 W. So these are available in your table if you do bottom up fashion. So overall, if you have not seen it or are not familiar, please work it out and complete this algorithm, because it's a max of 2 values. So you just have to go to your table, compute this. So every entry takes constant time, so many entries, so it's order NW time. Okay, not seen it, just please work it out. So this is faster, is it? Because the other algorithm we saw, try all subset, was taking order 2 power n times n, whereas this algorithm sounds like a linear time algorithm. Yes, it's a pseudo polynomial time algorithm. I didn't even mention that term, but yes, why? It depends on the value W, right? I don't like, the value can be completely arbitrary. Did we see a similar kind of analysis somewhere else? Network flows, when we saw the Ford Fulkerson first algorithm, we had an algorithm whose running time was m times the flow value, or the max capacity value. And quickly we moved on and said we don't like it. We gave a pure polynomial in n and m algorithm, and I argued that if you do shortest path augmentation, you can actually get a polynomial time algorithm for network flows. But here, this is a pseudo polynomial time algorithm because it depends on the values. So if the values are completely arbitrary, then this is not a polynomial time algorithm, right? And I had this example also for primality, right? When if your number, the simple square root of n algorithm depends on the value of the number, not the size of the number. Because to write down these capacities, to write down W, how many bits do you need? Log W bits. So you want an algorithm which is polynomial in the input size. The input size is something like n log W. Okay, so this is not a polynomial time algorithm, and we will actually show that this is an NP-hard problem. You don't expect a polynomial time algorithm. Okay, so this, since already somebody mentioned it, let me mention that pseudo polynomial because it's polynomial on the values of the input but not on the size of the input, because the size is log of the values.